on bending, bending of beams, namely. And I'd be remiss if we did if we talked about control bending things and did not have a really, what you call it, and not have a video of a bend, which is called of a bend test. So this is kind of analogous to when we were talking about strain and whatnot for normal stresses and such. We've talked about how to compute stress if you bend stuff like this, which is kind of awesome. And it's called like all those sensors on the wing are different kinds of strain gauges and whatnot that they use to evaluate stress at different points and along it, especially when it's bending to crazy angles like that. I mean, I would not want to see my airplane wings flex like that during flight. But the one thing that we haven't really talked about is, well, how do we get deflections and deformations of that beam? And that's kind of what we're going to be talking about more today. So let's play the game. So beam deflections, rock on. All right. So we're going to go through something called Euler-Bernoulli beam theory. So all these assumptions pertain to this particular kind of beam theory. And the trick about this is that it applies primarily to long, slender things. So things like bridges, roads. You can approximate some airplane wings, spars, kinds of stuff like that. Kind of the rule of thumb that I've heard is that height if you take a ratio of length to height, has to be greater. Usually has to be greater than 10. It's kind of like when we're dealing with thin wall pressure vessels, the radius to thickness ratio. It has to be large in order for the assumptions to apply. Large usually means an order of magnitude or larger, and or the magnitude is 10. So that's some basic stuff. Assumptions for this, lateral loads only. So like this would be a lateral load, right? It's something applied perpendicular to the long direction of the beam. Other assumption is, and this is partially covered by our length to height ratio here. So if I look at any cross section of this beam, they all stay perpendicular to the neutral axis throughout the entire bending process. So they don't deform or angularly, which in part leads us to this third assumption of small deflections. If there weren't if we didn't have small deflections, or if our fineness ratio was too low, that second assumption would not hold. So they're all kind of work together. Are we going to have to worry about how small a small deflection is? Not really. Not for what we're doing here. If you're bending stuff like metals and whatever, and it's a decent it's a decent enough size, so you're not going in like 5 times its length in what you call vertical deflection, because it's bending and stretching like a rubber band. You're not going to have to care about this. So all of our stuff will usually break by that point. So we shouldn't really have to worry about this too much. It's more just a FYI. You can't apply this to everything in the world, but for the general problems that we work with, it's fine. Right? Any questions on the assumptions? Great. All right. So this whole theory kind of starts off where we left off, starts up where we left off with our derivation of bending stress. So if you remember, like remember that guy, your favorite stress equation ever, might give you a lot of stress, as a matter of fact. Um, so we're going to start her there. Say for this cantilevered beam, this guy's just your radius of curvature. If you remember him, oh wait, curvature. There we go. I can spell, which is equal to like 1 over the radius something is, right? All right. So if I start with this, I know that stress is just equal to the elastic modulus times normal strain, right? Because that's what a bending stress produces. It produces a normal stress. Normal stress produces a normal strain because of Hooke's law. Excellent. Cool, right? And how do I want to say this? I know that strain varies. Strain when I'm bending varies. He's with height varies with height along the cross section. So if I have my neutral axis there and I measure it up from it, strain's going to vary linearly with y, right? So I could rewrite this as something like yr, or like y over rho, if I wanted to, which in the end gets me something that looks like 1 over rho is m over EI. And that EI is a very important term. And what do you think that it might represent, conceptually speaking? What does EI kind of, what do the components of EI kind of correspond to? Shape. Okay. So I is like your geometry, right? And E is what? The material. Okay. And if either of those increase, yes? Rho. Yeah. Radius of curvature. Yeah. Sorry. Yep, it's rho. I just like my radius better than theirs. Try not to have too many inputs. No, it's a rho. Maybe I should put a boat next to it. So if you have I as your geometry and E as the elastic modulus of your material, if either of those increase, would we consider the material to be what would the difference be if either of those things increased and then I tried to flex the material? What would the difference be?
It would be more rigid.
Be more rigid, be more stiff. Yeah. Any other thoughts? Cool. So yeah, it'd be if either of these increase and I try to flex this the thing's called the whole bar gets stiffer, right? Because we know that stiffness is directly related to both the actual stiffness of the material, so it's modulus of elasticity, but also to the area distribution. So often you'll hear about something like something called bending stiffness. And what they're referring to is actually the product EI. Because because it's, how do I say this? Because it's more of either one hand, you get the stiffer the beam is going to get. It would make sense that the that that would make the beam more difficult to bend. Words are failing me right now, but this is where we're going to kind of start from. Now I'm going to need some more room. All right, so we had 1 over rho equals m over EI. And if you work out a bunch, if you work out some geometry, you can get this relationship to pop out, which is super non-intuitive, weird, long, and mildly confusing until you do the what's called geometry. Yeah. Say again.
What is it?
This is y. This is x. So if I had a beam, or rather, and it was bending in some sort of like a circular shape with some radius of curvature rho, and I have coordinates x and y. The second derivative of y with respect to x divided by the cube root of 1 plus the square of dy dx would be 1 over the radius of curvature. Yeah. However, you don't have to worry about that because if you look at this equation, we can simplify it with a couple of assumptions. One of them is to ignore higher order terms. The idea being that if I have a relatively small number, and if I have this beam and it bends a little bit, so a little bit small, the angle between a horizontal line and the deflection is small, so less than 5 degrees or so, ends up being a very, very small decimal amount of radians, right? If that's a relatively small number, and the slope of a line would be approximately equal to that small number, right? For small angles, right? Because like you guys has all probably seen before. If I have tangent theta, it's equal to y over x. For small angles, this is my slope, and this is approximately theta. You guys have seen that relationship before? Yes, no, maybe? Okay, cool. Okay, so let's talk about that quick. So someone could get a calculator out and do a sine of 2 degrees and then cosine of 2 degrees, please. So we have seen that, right? We have been through what's called statics. Okay. or at least through geometry class. So that's like the definition of the tangent function. So if I say it, so if I say that theta is small, say it's like 2 degrees, sine theta would be?
34.8 times 10 to the negative third.
Say again?
0.034.
Okay. 0.034 times 10 to the negative third?
No.
Oh, 0.034, okay. Okay, and cosine hin would be?
0.99.
Cool. So, let's call it, and if you put 2 degrees into radians, can you give me a number, please?
What number do you want?
2 degrees in radians? It's, yeah.
Pi over 90.
I want it in decimals, please. Yeah. Thank you. So, here's the deal. For small angles, you're typically good until 10 degrees. I just chose 2 because I knew it would work out better. The cosine of a small angle is approximately 1. I mean, that's really, really freaking close to 1, right? The sine of a small angle is essentially the angle. So that means that the tangent of a small angle is just the angle divided by 1. All right? Cool. And because we call it change in y over change in x is like a slope, right? That means that theta for small angles equals the derivative of whatever function that you have, which in our case is the bending of, say, like the neutral axis of a beam. If I had some function of that and took its derivative, that'd be like a slope, right? We cool with that? Sweet. All right. So that means that this guy is going to be an angle, and it's going to be small. It's going to be something small. So if I take the square of a small number, does it get smaller or larger? If I take a square of a number less than 1, does it get smaller or larger? Smaller, right. So therefore this, I took a small number and I just made it even smaller. So one thing that you can do in a first approximation is that if you have something that's already small and you just raise it to a higher power, you can ignore it. So the upshot of this is that we can say approximately. Oh, come on! Don't crap out on me now. There's a 2 there, I promise. Wow, it just doesn't like that particular spot. We'll just go over here. Y dx squared. That's approximate. Means we essentially have that, which means that 1 over rho is approximately equal to what's called the second derivative of y with respect to x for small angles and all that stuff.
So the equation that comes from the tangent theta.
You can show that. So that whole tan theta thing was to illustrate why we can make this assumption and completely ignore that term. Yeah.
So what degree did you take?
We're getting there. We're getting there. Right now, this is just essentially it's the second derivative of the equation for the neutral axis, or how that beam is flexing. Yeah. We don't know it yet, but that's okay. Kind of like how when we started off deriving the beam bending stress equation, we didn't know the equation for anything there. We just kind of assumed it's going to go in a circle, and because of that, we can infer geometric relationships. We don't necessarily need to know what's going on until we're done. Once we drive towards something, then we can figure it out. So we got this. So if I substitute this in, we have d2y dx squared equals m over her EI. Sweet. And if you remember, what's the relationship between bending moment and shear force?
Shear force is the derivative.
Right. Hey, or you might say that like dm dx equals f shear, right? So that means that I can integrate and integrate and differentiate bending moment and shear force. I'm probably just going to end up with one form of the other. So going back over to here, that means I can start integrating crap with respect to x, because I know that elastic modulus is going to stay the same. Secondary moment of inertia should stay the same for a beam of uniform cross section, which is kind of what we're assuming. The only thing that's going to change is bending moment, and I know that is related to shear force. So, or alternatively, I know that I can come up with an expression for that. For example, if I have my cantilever beam, and there's a force down on the end, you could probably infer that the bending moment for any point in this beam would be something like that, right? Well, probably be a negative sign. Because this is just, you're going to have the same reaction force over here that you have in load, and it's going to change with x as you go out along the beam. There'll be a constant in there too, but generally speaking, this is what you got. It is, but the board didn't pick up the bit in the middle. Yeah.
I with like a lambda.
No, I'm not that. No, I'm not that weird. Well, maybe I am. I'm not that, but not right now. Oh please, no. So you can get an expression for m in terms of x, in terms of your position along the beam, substitute it in, and now we can integrate crap. Isn't it awesome? So let's work this out a little bit more. So if I take this guy, depends on what your load hood is. Like if you have like if you had a distributed load, we came out with a quadratic bending moment equation. But I mean, it's always going to be a function of distance along the beam, which reduces this to a calculus problem.
Yay, calculus.
Woo! So let's work with this. So if I take this guy, how do I do this? Okay, and I'm going to move the dx squared over to the other side. Because like dy dx or d squared y over dx squared, these are just variables. They're nothing special. It's just variables. So multiply by dx squared, and let's get everything in. Let's just get everything into the numerator. So we ended up with something like EI d2y equals mdx squared. Sweet. Let's integrate. So integrate once. Shame on me. Integrate twice. Sorry, that was bad. So integrate once, get like an EI dy equals and sorry, bounds are probably a good thing for what you call that side. Yeah. Oh, I guess that. Yeah. Right. Yeah. And have an extra one there. And you end up with something like that to start off with, which seems like a freaking horrible mess, right? Essentially, this is just saying, okay, we're integrating. Sorry, I should move this because I can only do one integral at a time. So this just means that there's some expression here that I still have to work out, but I know that I'm going to get a constant of integration, right? That's just how integration works. And the constants of integration in calc class, how did you normally figure out what they were? Well, I'm sorry. So the way you usually figure out these guys is based on boundary conditions or places where you know what the answer is. So, for example, so if I have my cantilever beam here and I'm pressing down at the end, what is the deflection going to be at the wall, at the neutral axis? 0, right. I know that y is going to equal 0 at the wall always. I mean, if it didn't, there'd be problems here. By the same token, this beam is fixed flat onto the wall, right? It's coming out from the wall and you bend the end. If we say that the cross section of the beam is always perpendicular to the neutral axis, is the cross section at the wall parallel to the wall then? Yeah. So the neutral axis at the wall, is it perpendicular to the wall or like almost perpendicular to the wall? Right, it's exactly perpendicular, which means that its angle of deflection is what? 0, which means that the first derivative at the wall is also what? 0, because the angle of the beam is 0. So now we have some boundary conditions, and if I slough that dx back over there, hey, look, I have a dy dx. So I could substitute in here and figure out what that first constant of integration is. If I had other, if I had a different problem, like one where I have a beam and say it's supported in 2 places with a pin, and there's some set of loads on it, I can follow the exact same sort of logic. These 2 supports aren't going to move. Therefore, the deflection here and here both have to be 0. So I still have a way to solve for these constants of integration that pop up. You just kind of use the geometry of the problem to your own advantage. And you can see it, and this will actually help us out in the same way as when you did statically indeterminate stuff, way like in chapter 2 or whatever, and strain helped us out there because we could say, well, these two things will strain together. Therefore, we can say, well, all this is going to equal 0, or we could find a way to get another equation like that. We can use this the same way if we had a statically indeterminate beam. So like a beam going between two fixed supports, because now we know 4 boundary conditions, right? Because there's no displacement or angular deflection at either end. So we can work this equation we can find the constants of integration and have 2 equations left over in addition to our 2 equations from statics. But we'll talk about more about that later. That's more of a preview of coming attractions. It's really cool. Anyhow, so back to work. We have our cantilever beam, force pressed down at the end. We said, cool. We've integrated this thing once. We have a constant of integration pop up, but that's not a big deal because we have boundary conditions, and then we can substitute in and find out what this thing is. If we integrate this one more time, so integrate once more, put a dx on this side where it belongs. Get something like that on the right hand side, and we're up to EIY on the left hand side. That's an I promise. Say, because you literally integrated this whole thing, and the integral of a constant with respect to x is that constant times x.
And then how did it do y? Like, was it dy dx one?
It was the integral of dy. So I moved the dx back over to the right hand side. Yeah. So that last step, let me redo it in slow. Let me redo it in slow motion. So I had y dy dx, right? And like that. So if I take this, multiply by dx, right? That moves back over to the right hand side. Sweet. And integrate. Let me take this from 0 to y, but you don't have to. Because in the end you get EI y C1x plus C2. Something like that. All right, and this guy might seem like a really wonky, crappy thing to have in the middle of an equation, but it's really not that bad because you'll have an expression for the bending moment in terms of x from your shear and bending moment diagrams. So you can just substitute that in and integrate to your heart's content. Just sounds awesome. And also this kind of illustrates where bending stiffness comes in, because if I take that EI term and I divide by it, so move it to over here, What happens as EI increases? Y decreases, right. And so as the stiffness goes up, the deflection goes down. So cool. That makes sense. Yes.
So the first integral, you do the x dx, so that's just equal x
Uh, this one. You do you do that one in second. So it's the integral of whatever this comes out to. Yeah, it's a double. Yeah, it's a double integral. Yeah.
The bounds for the first integral there is
0 to, yeah. I just erased the bottom of the 0 and I went across. Yeah. It's 0 to x.
same.
Yep.
So we can say like the function for a beam for the bending moment as like load times x, is what you're saying?
For a cantilever beam, yes. Well, for a cantilever beam like this, you'll have some reaction moment here plus some shear force, right? So if I took a section there, like that, it'd be whatever equation I come up with for bend, which would be like if this is P and this is M S, be like what? Minus MS PX, something like that. Assuming that's my positive direction. So it wouldn't be PX, but I mean, you can get an expression for it. Does that answer your question?
Okay.
Okay?
Mm-hmm.
Okay. Yep. It's whatever you get out of here. Yeah. Yep. I guess if I wanted to color code that, I could say like that. Assume that everyone can see red. All right. So that's the general equation. The trick is just applying it correctly, and this is kind of the this is kind of the beauty of derivations, because we didn't assume any kind of boundary conditions here. We didn't assume any kind of supports, except for the fact that we have lateral loads only. The only thing that we said here is that the beam's going to bend, and it's going to occur in some circular fashion. Each curve is going to be circular in shape. That's the only assumption that we made in terms of the geometry of the beam and the loading, besides fineness ratios. Anyhow, so this applies to any load case that you want to look at. If you want to look at a beam that has a whole bunch of loads poking at it, a beam that's supported in 3 different places, whatever, it doesn't matter. This expression still holds. So let's play around a little bit. Well, wait, not. We don't really have that much time. We'll at least talk about it. And also, if anyone's there thinking, wow, that was like a blatant waste of time, because you can just look in your book and they have all the equations written out for you in terms of maximum deflections of different beams, different supports. Like if you flip over to the appendix, I think there's a whole table in there. Let's see if I can find it, because this will actually be useful. Yeah, if you go to Appendix 666D, you actually have a whole page of which call our equations for the deflections of beams with all kinds of different kinds of supports. You have things for maximum deflection, slope at the end of the beam, all kinds of crap like that. It's called the value of doing all this math, because I thought the same thing like 8 years ago. It's called the value of doing all this math and being able to understand the math is because it's going to set you up to be able to adapt and learn later on for stuff that doesn't quite fit anything that's in your book or in your notes. It's like if you go on to mess with composite materials or something, which you will have to deal with at some point, because everything's starting to become made of composites. If you look at some of the drilling rig stuff that's sitting in the rock lab, they're starting to make those out of fiberglass. Being able to start to understand how to read math and is a really important skill. So I think that's actually where I'm going to kind of leave things off for today. Any questions about stuff?
No.
All right.